Hello everyone, welcome back to Course Edit. So in last lecture we solved our problem with negative numbers, and so for the limit, or you can say for derivative to exist for x to the power n, we just proved that x does not has to be 0 and n can be our positive, negative, 0, and it can also be a fraction. And we were stuck, or you can say we were about to solve for non-fraction, or you can say non-rational numbers. So basically an irrational number has to be there. So at this we quit our lecture yesterday, but before solving anything further we have to understand exponentiation and logarithm functions. So but before that we have to first solve our homework question, which I published it over here. So you have this homework question: modify and verify epsilon delta functions shown in today's code. So basically you had this code where you have this double f double x and 10 equals 2 and all, and you also wait. So basically that was the previous basically this was way beyond before that. So basically you had to solve for this function, f2 function, which was basically your discrete function for which you have to write your verify epsilon delta function. So you had to modify for this function exactly, which is your x double equals 2 return 5. So we can obviously solve this very easily. You can just remove that absolute of x minus c is less than equals to 1 e minus 9. So you can just do absolute of x minus c over here is less than 1 e minus 9. So what you can do, you can just solve this. So first let me explain what you have to do. So to properly handle this piecewise function, what we'll do, we'll just write f to x. Let's say the limit exists for x to 2 where it was supposed to be 4, but we have 5 at x equals to 2. So till this you'll have 4, and for 2 plus, and for 2 minus also you'll have 4. But for this exact function you'll have 5. X equals to 2, you get fx equals 5. Sorry, f to x equals 5. So this is your piecewise function, or you can say discrete function. So what you can do, you can just try to change this from limit x tending to c. You can have your fx equals to L. So we had this state that, so this states that 0 less than x minus mod of c, sorry x minus c mod is less than epsilon, delta, and you have this fx minus L less than epsilon. So which implies your fx minus c L mod is less than epsilon. And obviously you know that delta has to be, from here you can obviously see that delta has to be greater than 0 and epsilon is greater than 0 as well. So so what you can say, so this explicitly, so basically for this piecewise function it explicitly excludes the point x equals to c itself. So you have to exclude this. So what you can do, so you can just say that 0 less than x minus c. This implies that x does not have to be c. So basically this is already in that function, so you don't have to worry about that. So basically this by definition it is already there in the definition, so you don't actually have to worry much about this exact function. But let's say you had some other piecewise function, so that would have created some problem. So what you can do, you can just change the whole equation for your other piecewise functions. So let's say we have the standard functions are obviously like this, which you have it over here. So basically x times x. For a square function you have this f1. Let's say for f2 you have absolute of x minus. So basically I'm changing the equation like it was x at x equals to 2, you are supposed to have 5, but let's say at this, so let's say at x equals 1.999999 and so on. You have this. So after 12 decimal places, you can just have a 0 or 8, whatever you want. Let's say you have your 8 over here. Or you can say you can end it at this 12th decimal place. So you'll have this, which is actually, sorry, at 13th decimal place, not at 12th. Then you can say that you'll have this exact thing. And for this small change in this x, you should have basically you can return 5 in this f2. So basically for this x, which was your 1.999 and so on, you can return 5. Basically this is not going infinite times, so you just have to remember that this is going 13 times. 13 times. And let's say for this f3, okay, so let's say, sorry, this has to be less than 1e minus 12. So let's say you have this 10 times. Because for further, we actually won't be able to calculate much because there are limitations for your CPU. But obviously you can have that in a string, a vector of character, and then you can calculate it for even like 1000 decimal places or whatever you need. But let's not go into that for now. So we have this x equals 1.9 and so on for 10 times. And let's say we have a difference of, let's say we do 8 at the last moment. Then we have this f, let's say there is one more function f3, which is your function which is basically not neither continuous nor your piecewise. Basically it's piecewise but not completely piecewise. So basically for longer this, you can just change it to this. Basically what I want to say, for x less than 2, you can either make it a constant equals to 3, return 3. Basically this is also a piecewise function, but by definition, yes, it is. But let's call it a function that is a combination of two different functions. Basically that's what piecewise function is, but yes. Otherwise you can just return whatever you need, 7 over here. So basically these are two constant functions. We just combine them in a single function. So which are like this 3 and 7. So okay, sorry. So this has to be 3 and this has to be 7. So for x less than 2, we have this 3, and x greater than 2, we have this greater than equals to 2, we have this 7. So let's try to write for these functions and see what our code should look like. So let me first explain what our code should look like. So suppose you have a few samples, let's say 200 samples, and you have your step. Obviously you know what your step will be. It will be basically delta y samples. By now you should already know what your steps have to be. You can just obviously change these steps, these samples. So the sample rate can be changed directly over here. So that's the reason we are taking sample over here, so that we don't forget how to change, where to change the samples, or you can say the sample rate, or you can say the steps rate you have to change, which are your samples. Yeah, so we have this for function in which you can just have your x equals c minus delta. So instead of writing delta again and again, I'll be just taking symbols. So this x less than c, x plus equals to your step. Let's call it step only. So you have this. Let's say absolute value of this x minus c is less than your 1e minus 12. Here it was 1e minus 9, but we are taking 1e minus 12 for our the thing we have changed over here. So we are taking 1e minus 12, and obviously you can continue with this. And suppose if there is a function fx minus l, so for the function you can just obviously write less than epsilon, then you can return true. Not true, we can basically continue this, and if there was no problem we can return true at last. Otherwise if there was some problem, let's say this was greater than equals to, then we can return false directly over here. So instead of writing 2 times, we'll be just directly writing greater than equals to epsilon, and then we'll just directly return false over here. And for less than, you'll just have your you'll have this for loop ending, and you'll have your absolute of fx minus L less than epsilon. For this, you can just return true over here. Basically, by definition, obviously you should check in your notes. You'll have the definition of your this was sigma epsilon delta definition. So, or delta epsilon, whatever you want to call it, but it is actually said epsilon delta definition for a reason, because epsilon is chosen first, then delta is being calculated afterwards. So that's the reason it is called epsilon delta definition. Anyways, so you have this return false, true, if this is less than your epsilon for every case, basically for each of these x minus c. Then you have this true over here. Yes, so basically you have this return true. And obviously if it is less than c, then if it gets equal to or greater than equal to c, then you will get out of your for loop, because we implemented a condition over here, x less than c. And x is always changing to your c minus delta, and this always goes with plus equals to step. So basically that will just help us in several ways. So you have that. Now what you want to do, you can basically check this function whether it is giving the correct answers or not. So you can run a test. So you can create a runTest function, which will basically you'll have to let's say we take a string name. In that, we can basically take what our function name is. Suppose if it is a square function or something, then we can just directly see out over here. Otherwise we'll have to see out directly below this, like in the main function, but we can just take the name and directly see out over here in the console. So we have our double c, which is your a. So if you remember, a was equal to our c, so you don't have to panic if you don't get what c is. So it is basically the constant which is equals to your 2 or whatever you want it to be. So double c, so you have this, then you have your double c, then you have your epsilon. So let me just write these symbols for now, delta, and you can also take some function which is your complete function over here. Suppose this function you want to take fx, then you can take that as well. So to do that, you can just take you can just write this data type of that function. Suppose I write double. So basically let's say f3 was a double function. Where is f3? Yes, so basically this was your double data type. So what you can do, you can just write double, and then you can just take function, and then you can write double inside that. So what it returns, what the function was initiated as, what the function returns, and what the function is function is basically this. You have to just take this, and these two are your parameters, you can say, in a way, which is first parameter is your data type and second parameter is your return data type. So you have this. So basically, obviously you have to take this double to initiate this function inside this function. This double, just like these double and a string, you have to initiate this over here, and this is your property to a function, the return type. So that's what you have to do. Basically, when I'll be coding, you'll just get it in an instant, so don't worry about that. For those who don't understand this directly written code, for them I'm explaining it over here. So what you can do, cout testing. Obviously rest you know what I'll be doing, cout testing and all. Cout some text over here, then we can just say if verify epsilon. So basically we are writing this function just so that we can just write everything in a single go. Epsilon delta. So we'll be defining a universal function. So let's call it a universal over here. Universal. Let's say we have this verify epsilon delta universal, where we'll be just obviously taking CL delta and all, epsilon delta and your function, and then after that we can just do this. We can just see out verification successful. So basically I'll be writing that, and I'm just putting 3 dots over here because I don't want to write everything over here, because we should move directly to our console /n, else just see out that it was unsuccessful. So let's run the test. So basically this run test was not necessary, but since we are going to implement multiple functions, so we'll be just needing that. So we need that as well. Okay, so let's start with the functions. So let's say this was f1, this was f2. Let's change f2 to our absolute of x minus, let's say we had, okay, so let me put the mic over here so that I can write properly. So we have x minus 2 dot o. Then we have our less than symbol. Okay, so less than 1e minus 12. Basically this is 10 to the power minus 12 if you don't know what 1e minus 12 means. Obviously we can return 5. Basically this is a double function, so we should return 5.0 instead of returning 5 directly. Otherwise we can just return this x times x. Otherwise we have our f3 function. So f3, which is basically your double. So you have this double x, which will be your if absolute of x minus 2 dot o is less than, sorry, if x is less than, I think this was not the f3 function. What was our f3? Yes, so it was x less than 2 dot o. Then we have return 3. Otherwise we can just return. Otherwise we can return 7. Basically we don't have to write conditions again and again. Basically this was less than, otherwise it will just take greater than equal over here. So we don't need to write any else statement. Okay, so now I think it looks very good to me. Okay, so this has to be fixed for now. Okay, so instead of writing this epsilon delta, we'll be just taking universal. Then we'll have double C, double L, double epsilon, and what all we have? We also have your delta. Okay, so we also have your delta, and what you can do, we can also add double function, and then we can just, okay, sorry, that's not how we declare a function inside this. So we have a star function. So we are taking a function star because we want exactly that function to be called, instead of creating a different copy of that. So we have this, and then we have double. So we want to call exactly that function. And obviously we have our this function x. Obviously if you want, you can just take some other name. Suppose if you want just to take the name f, you can just star f. Otherwise I'll be taking function because I like that. Actually this is giving much problem. So instead of doing these two views, I think I should have done a single view. But yes, I mean, you can just copy this, right? You can just pause and copy that if you haven't understood. So we have this, instead of step, let's call it double sample equals your 200. So I'm taking exactly the terms which are used in data science. So the sample will be your sample for your parameters which you will be taking in your libraries. So we are first understanding how libraries are made, then we'll be implementing the real libraries which are actually created by those great developers. So for now, just bear with it. We won't go directly to the library. Well, let's keep the talk for later and let's implement this for now. So we have sample. Let's say it's samples. Let's call it samples. We also have for double x equals c minus delta. Let me just check. For x equals c minus delta. Yes, x less than c. C plus. Okay, so we have something wrong over here. So we don't need c plus delta. So yes, obviously it was wrong. So if we have absolute of x minus c less than 1 minus 12, let's do it minus 12. We can continue. Let's say if we have absolute of, okay, so we need to say a function x minus l. Basically, we'll be passing the parameter f3, f2, and f1 in our this function directly. So we have function x minus l greater than equals to your epsilon. And then you have return false, return true. Okay, so instead of returning true directly, let's say we want to go from c to c plus delta in a second go. It's just done because we need some samples for our, basically from c to c plus delta, we need a different, basically the calculation has to be the same, but the approach has to be a bit different. So I'm thinking if the calculation has to be same, let's not complicate it. Let's say we just directly do this as c plus delta over here. But obviously later when we want to implement different functions, we'll be changing this as well. Basically we'll be implementing from c minus delta to c over here, then from c to c plus delta we'll be implementing a different function. You'll understand why we are doing that. Basically if you know our limits, then you know that there is a 0 plus and 0 minus limit. Basically if you know the L'Hopital rule, you should get some idea why we'll be doing that. So for now, let's keep this simple like this. We have this, and we also have one more function, I think. Yes, so we have this runTest. Basically, instead of writing this multiple times, we'll be just directly writing that. So we have our runTest function, void. Yes, let's take it as void runTest. Okay, so today we are actually taking much longer to write the code. Okay, so let me just check how much. Okay, so we are already past 22 minutes. So we have this string name. Obviously, the good content has to be delivered in a decent way. So we have this. So where was I? It's a string name. Then yes, let's go with double C. Let me just copy it over here. This function all. For some reason, it directly teleported. Anyways, so we have this. And obviously we need a curly bracket. Well, now I can't see my own function. Okay, so Google Collab has built something like a different thing. Anyway, so we have this. Let's say we have cout. Let's say we want to say testing your limits. Instead of writing testing your limits, let's say testing. Let's say we have a name. So let's give some space. Name, and then we can just have this, and let's say we add a single colon over here. So colon helps us to it helps us in nothing, but we just use colon for some reason. Also we need universal function, so we have this universal, and obviously we are going to pass some parameters. Let's say we have c, l, epsilon, delta, epsilon, and then delta, and then we have our function. Let's say we have function as it is. Okay, so it again disappeared. Well, it's not a good thing that's happening. Let's say we have cout verification successful. Well, basically this is a boolean value, so it will return true or false. Based on that, if it is true, then we'll be saying return will be we'll be having this as the output in our console. Verification successful, verification successful. And let's say we have something else. Let's say verification successful, and let's write a few more things. Limit is good. Haha. Well, actually, let's remove haha. We can just have this. Else we can just see out verification failed. Verification failed. Verification failed. Complete your degree first. Complete your math degree first. So thank you. So let's have this. Okay, so it again disappeared. Every time I'm trying to press enter, it just disappears for no reason. Basically, it just moves upward. Let's try one more enter. Okay, so here it didn't go like that. Basically, it's happening inside this function. Let's try it over here. Okay, so it didn't work over here as well. So it's only happening when I'm out of this frame. Basically, this line is the frame, I think. Or maybe just this frame is problematic. Yes, so that frame is problematic. So I'll keep that in mind. So we have this. Let's remove this. Let's see out. Let's keep that as well. So yes. Let's say we have delta as this. The smallest neighborhood test. We have our delta. Okay, so we have. Okay, so just wait. Let me just put on the charger. Okay, so actually it was already there, but it was just the switch was off. So we have this cout, set precision and all, and then we can just run the test. Run test. Let's say we have our standard function. The standard function for square. For power n. So for x to the power n, let's say. And then we have this, we have to pass everything. So I'll be copying everything like C, L, epsilon, delta and all. So we'll be just doing C, L, epsilon, C, L, epsilon, delta. And we also have F1 over here. For the standard function, we have this F1. I think I should name them standard and all, but let's not worry that much about them. Let's press enter, and then we'll be like teleported to upward. Yes, so we were teleported. So we have this run test again, and then we have our standard function. Also, let me just copy this. Instead of doing this again and again, let me just paste it directly. Yes, it looks very good. So we have our removable discontinuity function. Basically, okay, so let's say discontinuous function only. Discontinuous function. Let's say we have mixed function. Last function is mixed function only. So we have this F3, and we also have this F2. We have this F2, F1, F2, and F3. So I think we are now like got to press enter. Shift enter. So let's try to compile this now. Let's see if we get successful answers. It's taking time. It's actually okay. So I didn't actually. Okay. So I have to run every cell for now. Basically, I didn't connect to Google Drive. I forgot to connect this before the lecture. So Don't worry much about that. It'll take some time. So after it gets it gets executed, before that we can just study something else as well. So yesterday we left at our this exponent and logarithmic function. So for logs, you have studied logs, right? Logs are basically sometimes to the power e to the power 10. Okay, so we are having few errors. RunTest is standard function, double C, double L, double epsilon, double delta, double star function, double. Okay. Wait. Okay, so this is double as well. This is double. This is double as well. What is this single star doing over here? From function double 50th line, I think, right? Line 50, I can't see any function actually. Okay, so actually I can't see any function, but I'm having some problem over here. Just wait for a second. I'll be able to debug this right now. Okay, so let's check for both. If we have this over here, let me just come over here. Yes, double function, double function, double. For some reason, this looks bigger than our verifying function. Sorry, this runTest function. So why is that? Okay, so the name is actually very large. So this is double C, double L, and all. Yes. So what is the problem? Let me just read the problem. Error invalid conversion from double star double end to double comma end. Oh, okay, I got it. So basically over here we are just having two parameters, but there we passed for a single parameter. Let's just reduce this and let's write it over here. Int n equals 2. Int n equals 2. So basically this will just give our square as well. So now we can run this. Okay, so it finally executed. So testing epsilon, you can see this was 0.01 and delta is this at the start of the function. Obviously delta doesn't change, your constant changes. So you have your testing standard function for x to the power n. Then we have verification successful, verification failed, complete your math degree first, thank you. So basically for mixed function we don't have the correct delta. So basically the function is right. Basically our delta was actually derived for our continuous function. So that's the reason we are getting this. Complete your maths degree first. So don't worry about that. It was supposed to happen. Because you can already see that for x less than 2 we have 3. And then for x greater than 2 we already have 7. So 3 and 7. So this was bound to happen. So don't worry much about that. So basically everything is working fine and correct. It's as fine like a wine. I mean let's not say those things, but yeah, we have this. So let's go to our calculus part. So you are able to finally check these functions, and these functions. So this is how you actually check your wrong answers, and then AI actually implements them back to that, and then it verifies everything, and then it just returns a single value. And if it's wrong anywhere, then it can just have a single output. But since it's in LLM case, you just have multiple outputs. That's actually good. Basically, it connects the output. It doesn't create any output. Basically, it has taken some word it. Sorry, not if it is a word parameter. Basically, if the parameter is set to a word instead of letters, then it'll just take it am necessary. So basically, if it is not trained enough, then it'll give some answers like that. But suppose if it's trained enough, then it'll have it is /r necessary. But word model, or you can say the letter model, basically every character it checks whether what has to be there. So those models are great as well. But I've heard some other model like folder model. So folder models are actually very good. So let's not talk about that for now. Basically, folder model just takes everything in your folder and it tries to basically take tokens like a folder, and then like it just first takes every file text or any file, and it will read throughout that, and it will try to break every part into your this word model. Then every word model gets hit by a parser, you can say, which then converts it into a letter model. I mean, I'm just giving names, letter model and word model. Basically, they have different names. But yes, this parser is actually a right name. But yes, these word and letter models are not something that you will hear often. So basically, these tokens are like folder model is actually very good. Actually, I don't want you to just go and search in between the course. Otherwise, it will just break your flow. So that's the reason I'm not taking the correct words. So don't worry about that. We'll actually be covering everything. So that's a good thing. Wait. Okay, so should I keep it just this much? Okay, so we have already passed 36 minutes. I think this should be enough for today. Let's just start some let's start a bit of our exponential function and all. So obviously I'll be explaining you why differentiating e to the power x is not necessary. We can just prove it and all. So instead we'll answer a deeper question. So the first question I'll ask, why is a number like e so special that its derivative equals itself? So if I ask you d of e by dx equals what? Oh, sorry, e to the power x equals what? Then you should have an answer. Remember what e is. If you don't know, let me just explain you with an example. So I'll be just explaining e in this lecture. We'll be talking about the complete proof and all in the next lecture. And remember that, okay, so let me first explain. So the motivation was basically this banking sector had some problem. So basically you had something deposited in your, imagine you have to deposit something like, oh, so let me not write everything. So imagine you have to deposit 100 rupees or $100 or whatever you want. So let's say you have this 100 coins in your bank at 100% rate, at 100% annual interest. So you know what annual interest does, right? It is basically an interest paid over year. So it depends on you how you want to pay that. So suppose if interest is paid once a year, interest is paid once a year. Okay, so let me just write it in simple language. Once a year. So for once a year, you have this 100 times 1 plus 1, which is your 100. Basically, you should remember the formula for your CISI. Basically, simple interest and compound interest. So basically, we'll be using compound interest over here because obviously we are going to go with the compounds. So once simple interest and compound interest are basically one and the same thing. One is basically for a year, and again we have to just put that, and one is basically your the interest divided over year. Basically it is divided in months, and you paid once the year ends. I mean, it depends on the bank how it takes. But yes, interest doesn't depends on the bank. It is universal. So let's say interest is paid twice a year. Okay, so why I'm writing instead of, sorry, once an year and twice an year. Or yes. Okay, so instead of taking let's twice an year, once an year, twice an year. So we have this 1 plus 100, this. Then you have half year earns 50%. So 100, 1 plus half will be your, then you can just take square over here. Basically you are just doing 1 plus, this is your formula, 1 plus 1 by n times n. Sorry, to the power n. So basically you just keep doing this n times for an interest, because your interest was divided in n parts. So you just keep multiplying that part with the previous part and you get the final this value. Since it has to be same, like it has to be consistent, instead of like increasing 1 plus 1 by n plus 1 by n plus 1 and all, it has to be consistent. So we can just do this. I'm not going to prove the formula for interest. You just have to remember that what E is. Instead of writing all this, let me just directly write what E, how E was derived. So basically we had something like limit n tending to infinity, 1 plus 1 by n to the power n. So basically this was called your E. No extra knowledge is needed over here. So, and you finally got E is nearly equals to your 2.718281828 and all. Then you can notice that nobody had invented E. It just basically appeared naturally from a limit, and just like pi appeared from your circle. So you have those intuition inside you. So let me just ask for an intuition. So why does the money stop around 2.71828? If you can answer this, let me just know this in the comment with what you think, basically what your intuition says. With your intuition, you can just write anything in the comments. So comment the answer. So why does this stop around this? Well, basically it is going till infinity and this is going till infinity, right? So, but you know that this is the power. So why does it stop? Like it should have stopped something around 100,000 or something. I mean, if that's the case, then also you can say. Otherwise, you can just try to explain it mathematically why this happened. So please do comment your thoughts. And I don't want an answer. I want just like normal thoughts, logistic thought. So thank you everyone. Thank you for watching. Let's meet in the next video. Basically that will be uploaded on Sunday. So yes, let's meet there. And obviously you'll have a homework question pinned in the comment. No, not pinned in the comment. You'll basically have it in the description. So let's meet in the comments, I would say. Thank you everyone. Thank you for watching.